Hi students, Dr. Vic here, and this brief video will introduce autocorrelation and how you can correct it. Now this is a very rudimentary introductory video. It doesn't go into all the complexities of time series analysis, but it gives you a few tools to think about if you happen to be working with time series, and gives you some of the methods that we'll be doing in this class for some of our simple adjustments. So autocorrelation, this is a problem that comes into play when you are working with time series data. It is a problem with error terms. So time series data, maybe you have year by year price, quantity, income data. In the example I'll give in a minute, we'll look at cigarette sales and prices over a number of years. Now, the problem is, if you think back to your blue conditions for OLS, to getting the best linear unbiased estimates, one of those conditions relates to error terms in your regression. And error terms should be kind of randomly distributed. If you start seeing that one observations between error terms with connected to various observations or correlated somehow, it throws off these blue conditions. Typically in cross-section data, that might be called heteroskedasticity. Well, a special form of that comes into play when you're dealing with time series data, and this special form is called autocorrelation, and it's specifically when the error terms of one year are correlated with the others. So you might be able to detect this when you are seeing that error terms for consecutive years are following some kind of pattern. So what this does to your regression in terms of the coefficients that you estimate, it does not necessarily bias them. Okay, the coefficients themselves may be unbiased and consistent, but the problem, since this is an error term problem, it does lead to biased standard errors of those coefficients. So if you have biased standard errors, you may the precision of your estimates may be off, and your statistical testing of whether something is significant or not may also be off, leading you to think that maybe your estimates are more precise and statistically significant than they really are. So to correct these, we do a number of steps, and I offer a couple of steps for you to do after you perform your regression. First, we look at the Durbin-Watson test statistic. This test statistic usually ranges from 0 to 4. A rule of thumb, again, a simplified rule of thumb. If the Durbin-Watson statistic is near 2, you have a good feeling that autocorrelation is not present, it's not a problem. What we're looking at precisely is typically in these time series analysis that economists do, the problem with positive autocorrelation. If instead that Durbin-Watson test statistic is closer to 0, between 0 and 1, that's an indication that autocorrelation is problematic. You're having these correlations between your error terms and your regression. So what you want to do is run your regression. After you run your regression, you can estimate your residuals. You can plot those residuals over time and see if that pattern emerges, and I'll show you that in a moment. After you do that, in the same time you want to estimate your Durbin-Watson test statistic, which you can do easily in Stata. Then you plot these residuals and see if that pattern emerges. There's two ways to adjust for it once you have established that autocorrelation is probably a problem. The standard one is, one of the problems going on here is the variables themselves are somehow dependent on last year's amounts. Okay, for example, this year's prices have something to do with last year's prices. This year's income levels may have something to do with last year's income levels. So you introduce a number of new variables. Your outcome variable lagged by last year, and your independent variables lagged by last year. So let's say if you have 2 independent variables, you'll now have 4. The 2 from this year and the 2 lagged from last year. Those are additional controls that are helping explain what's going on in your regression. And you would also lag it on your outcome variable based on last year's outcome variable, because this year's outcome you need to control for last year's. So we do that simply in a straightforward fashion using the price command in Stata. What that does is that also estimates a adjustment coefficient, an adjustment factor, which is called rho in the literature. If you can introduce that rho, that's going to form a statistical correction for autocorrelation. Now, typically what we see in many econometric problems is this rho is close to 1. And if rho is close to 1, you can simplify this adjustment, your regression adjustment for autocorrelation. Instead of running a regression on your 3 variables as they were before, or your more numerous variables based on lags, you can run a regression based on the difference in your outcome variable on the differences in your independent variables. Okay, so it's basically a regression on how much does y change given how much x is changing in your data. So I figure an example in Stata might be nice to walk through now. So I'm using the cigarette data that we have looked at before. I'm going to assume that you can input that data, bring that data into Stata, and this is similar code to what you've seen before. So I have my Stata cigarette data. This is cigarette taxes, prices, and quantities. What I'm going to do here, remember the original data had many years across many states. It was what we called panel data. I can transform this into a time series data if I don't have that cross-section across all states. I'm instead just going to look at Pennsylvania. Okay, so now I have data just for Pennsylvania. I have Pennsylvania over a handful of years. It's not enough to really do any analysis with, but we're using this as an example. So we have by year Pennsylvania data. This is the price of, this is the income levels, this is taxes, this is prices. Okay, so again, what we're going to do here is we're going to tell Stata that this is a time series data set. Last time we told it was a panel data set, but it's not a panel data set anymore. It's a time series. So we'll run this TS set that tells Stata that we have a time variable from year. It ranges from 85 to 95. I'm going to go over here and I'm going to generate my demand level equation, my demand level variables. Quantity is packs, income is adjusted for population and CPI, and then price takes out taxes. Now, what's going on here? Well, let's look at a couple things. You see that income is going up over year. So you see that year is here on the bottom, 85 to 95, and incomes are steadily rising. That's an indicator that time is influencing income. That's another blue condition problem. If time is a omitted variable, but it's coming into our regression and having effects, that's problematic. Looking at price, you get the same thing. Prices have this really interesting relationship to year. If you do a correlation, you start to see very quickly that income has a very high correlation to year, and year has a high correlation to price. So time is going on, something is going on here with time. So that's the first indicator. Simply working with time series data, we should figure that autocorrelation could be a problem. There's this relationship with time in our data. Running the regular regression, as we've done before, we get some coefficients. I don't want you to look so much at the coefficients as much as I want you to know how to identify for autocorrelation. So again, we ran our regression. Let's check for this Durbin-Watson statistic. This is, after you run a regression, estat d Watson is the command. And as I said before, a Durbin-Watson statistic near 2 suggests we don't have autocorrelation. Something between 0 to 1 is problematic, and our statistic here is 0.81. So that's indicative that we have some positive autocorrelation going on. Going through this further, again, we can look, it's a problem with errors over time. So I'm going to use Stata to to compute the error terms from the regression. And it's predict, and I give this a name. I'm calling it errors and telling it to predict the residuals for each observation. And now I'm going to do a scatter plot between those residuals and year. So here I have the residuals, here I have a year. So this is a nice graph that is indicating that we do indeed have positive autocorrelation. You see, as year goes along, this thing is steadily rising. It pops up and then it steadily goes down. So these error terms are related in this nice kind of wave-like pattern. So between the Durbin-Watson statistic and this pattern of the errors over time, we have a good idea that this is going on. Next, now we have to correct it. Again, the first way we correct it is using this price command, where we do a longer regression. What price is doing is it's going to regress quantity not only on P and I, price and income, but the lags of those variables as well. So price is doing this, and it sets it up for us in a really nice way. Now these are autocorrelated corrected coefficients. We could go forward thinking that these are good ones to go with. But what we want to look at is, what is this row? So this row, again, it's in this example, it's not exactly, it's a little bit further from 1 what we'd like, but we want to see if this is close to 1. If this is close to 1, then there's a simpler way to adjust our regression for autocorrelation. So I'm going to show you that, despite this being problematic. If we were just going with this data, again, there's only 11 observations, so we wouldn't be. It's just an example. But we would think about these in terms of elasticities, etc. But instead, I'm going to show you the second way of fixing this, and that's doing the same regression but on differences. So you see here, I'm not doing a regression on Q, P, and I. I'm doing a regression on the difference in quantities, the difference in prices, and the difference in incomes. So the D dot, that's telling Stata that I have time series data set up, and instead of looking at just Q, I'm looking at Q in one time period minus quantity in the next time period. That becomes my new dependent variable. And I'm regressing that on prices in one period minus price in the previous time period. That's D dot P. And I is for income, one period's income minus the other. So this is three variables that we're regressing, okay? So I'm going to regress that, and you do that without a constant as per the literature. And so this is getting me what should be a corrected regression estimates. Again, it's close to what we had before, but it should have unbiased standard errors. Now, what you want to do is you want to check your new regression. Let's do the Durbin-Watson statistic for this. And now we see that Durbin-Watson is closer to 2, suggesting that we successfully adjusted for autocorrelation. If we predict errors again, I'm going to do make a new variable here to predict errors on the residual of this this new equation, and I'm going to do a scatter plot. So we no longer have a consistent pattern. Again, we still have a bit of pattern over here, but it's not as obvious as it was before. Again, this is imperfect data and an imperfect example. But again, I wanted to show that this is the process you go through. You'll do this in your homework. You'll do this in your demand equations. All right. Good luck with everything.